Thank you all so much for having me. I really appreciate your time. And in the time that I have, I want to give an analogy. I want to craft my talk around this analogy. And it was an analogy that I first heard about improving scientific expertise about any topic. And it was imparted to me when I was 18 years old, starting as an undergraduate. And it involved a wide open ocean of things you don't understand. So that's what my assigned mentor told me. When you first start trying to learn physics, you understand nothing about it, and there's a broad open landscape of things you don't understand. And as time goes on, maybe you understand separate concepts, but there's a hidden landscape that connects them, and those connections are hidden from you for a long time. As time goes on, you not only understand more total information, you start to see this previously hidden network of concepts that connects seemingly disparate topics, what appeared to be seemingly disparate topics before, until finally, hopefully, you approach a full understanding of whatever the topic is you're interested in understanding. And this is the analogy that I'd like to use to talk about where we are in the field of exoplanets right now. And so this is sort of showing the sum total of our intellectual landscape of exoplanets in 1995. So we discovered the very first planet outside of the solar system that is orbiting a main sequence star in 1995. And with it came the understanding that the solar system blueprint is not a universal one. And that's because the first planet that we discovered around a main sequence star was a Jovian-sized planet parked very close in to its host star. So now we know at least that the type of way that nature forms planetary systems is not always uniform. By 1995, we not only understood that some stars hosted planets, we had constrained the number of sun-like stars that hosted planets in orbits like that first hot Jupiter to be around 1%, a number that I'm going to visit later in this talk. And we knew that maybe even tens of percents of planets hosted stars of some kind. Moreover, we knew that it was possible not only to detect planets unto themselves, but to detect the molecular signatures of their atmospheres. In fact, the very first detection of a species in the atmosphere of an exoplanet wasn't a molecule at all. It was an atomic line of sodium, and that was in 2002. And we knew at this point, too, that it wasn't only sun-like stars that host planets in the main sequence. It was stars across all spectral types. We were starting to get some kind of understanding of that. And finally, we were starting to link together something of observational information of how planets might form as encoded by the content of the stellar atmospheres. So based on the metal content in the stellar photosphere, there appeared to be some link between that and whether or not planets form at all. That is hot Jupiter planets. Here's where we were in 2015. So this is sort of up-to-date information about exoplanets, sort of the state of the field presently, give or take, is that we know the raw occurrence rate, which is to say, as a function of orbital period and the radius of the planet, how many planets occur per star across different spectral types. That information is not complete, but it's more or less complete for planets down to 1 or 2 times the radius of Earth and out to orbital periods of an AU or 2, depending on what exact method you're talking about for the detection of planets. We had gone beyond the detection of individual molecules to even the detection of particulate sizes. So, for example, the particulate size constraint in the atmosphere of a super-Earth, something like 2.5 times the size of the Earth at 500 Kelvin. We've detected, we know like a lower limit on the particulate size, or in an exocomet, we've detected particulate sizes. So it's not only now molecular species, but also grains. We've seen pictures of planets. So that was 2009, was the first time it was in my second year of graduate school that we saw the first image of exoplanets. And some of those images are very, very famous. And finally, we learned not only that presumably the content of that primordial disk, which gave rise to both the planet and the star, it's not only that it affects whether planets form at all, it also affects how they form. So we started to see links between the presence of planets and also their orbital dynamics. Seemed to be encoded in the stellar metallicity. So let's say that we had some goal for where we wanted to be as a field in 2040. So these, I think, are arguably achievable aims for exoplanets, things that might appear on the front page of the New York Times in 2040, arguably speaking. And the first is, not only do planets occur at the right distance from their host stars, that water would be in its liquid form. Not only are those planets terrestrial in nature, but something beyond those two things that speak to ultimately the habitability of planets. So it's hard to say what gives rise to the evolution of life, but Carl Sagan said that it requires a murky puddle, probably, and a murky puddle requires a couple of things. You need liquid water, and you need a terrestrial surface on which to lay it, and presumably an atmosphere to protect it. So starting with those things is interesting, but more complex questions of habitability involve things like plate tectonics. Perhaps we will have detected how commonly so-called biomarkers occur in the atmospheres of planets, and that's a complicated question. When people talk about biomarkers, they're referring to life, but life as we know it, generally speaking. There's also life as we don't know it. However, in conversations about what qualifies as life, obviously it's a wide variety of parameters, but generally speaking, you require life to extract chemical energy from its environment and replicate itself. And there's a limited number of molecules that can do that. It's not infinity. It's something like 20,000. So we can assess how often those molecules occur in the atmospheres of planets. We'll understand, too, how stellar activity imprints upon atmospheric chemistry. The Earth itself has not been a static place for life to be nourished. And also, potentially, the detection of microbial exolife, something which I'm sure will be argued about for decades, but I anticipate probably that might appear, a claim of that nature. So if we wanted to be in that place at 2040, what are the questions we should be answering today? And I want to answer 3 of those questions. These are questions which are only answerable once you get to a state of the field where you have hundreds to thousands of exoplanets. And it's a point at which I totally pivoted my research program a few years ago. I built my own career as a graduate student in the early part of my career on individual planet discoveries. And I don't know that I will ever publish an individual planet paper again. They're no longer kind of as impactful as they once were upon the field, because we can answer these types of big questions with more than one planet, with dozens to hundreds of them. So first I'll answer, what is the typical type of planetary system in the Milky Way? Is it anything like the solar system? Secondly, how dynamically stable are these timescales, are these planetary systems, and how does that dynamical timescale compare with the putative timescale for life to evolve on the surface of a planet around the most common type of planet host, which is not like the sun at all? And moreover, once we've established how often rocky planets occur with murky puddles on their surface around the most common type of planet, how long do those atmospheres last? Are they present at all? And this is something which is also constrainable, as I'll talk about in the end when we speak to TESS. So first, talking about the typical type of planetary system in the Milky Way. In any talk about exoplanets, I think it behooves us to start with our own home, with the solar system. And this gorgeous movie was gathered from NASA's Solar Dynamics Observatory in 2012 during the transit of Venus. And you can see that Venus transiting, this event takes about 13 hours, so this movie is sped up, is not the only dynamic part of this movie. You can also see, in addition to the path of Venus crossing the face of our host star, something of the rotation of our sun, and also this beautiful detail of the roiling surface of our host star. And yet, even if all of this beautiful resolution was collapsed to a single pixel, and you were removed at infinity, you still could infer the presence of Venus because of the tiny fractional dimming of Venus blocking some fraction of photons from reaching the silicon eye of your detector. And that method of finding exoplanets is called the transit method. It did not used to be the method by which we found the most exoplanets, but it is today. And that's because of a singular NASA mission called Kepler. It's easy to describe how Kepler worked. It was a silicon eye. It affixed its gaze to a part of the sky, which is overhead around midnight in the summer months from New York. And it didn't look away for a period of about 4 years. It's about the size of your hand held at the end of your arm. And this is the sum total of our knowledge of the existence of transiting exoplanets in this part of the sky prior to the launch of Kepler in 2009. So this is actually a cluster of stars. We knew about the existence of one single Jupiter from a ground-based survey prior to the launch of Kepler. 4 years into the end of the mission, so the nominal Kepler mission, these are the locations of planets that we have found. Now keep in mind that transiting planets have to reside in that perfectly fine-tuned geometry. So this is also only a fraction of the planets that reside in this part of the sky. These are only the ones for which we have that geometric luck worked out in our favor. And there are 2 things I want to impart. The first is that the types of planets we were sensitive to from the ground, which were these giant-sized planets, Jupiter is about 10 times the radius of Earth, are actually intrinsically rare here. They're about 1% of stars around, or they reside around about 1% of sun-like stars. But the vast, vast majority of planets are intermediate in size between the Earth and Neptune. And my colleague Leslie Rogers likes to say that these are 80% of the planets in the Milky Way and 0% of planets in the solar system. So it's just that the types of planets we were sensitive to from the ground were only the lowest of the low-hanging fruit. And all of these extremely tasty planets were just outside of our reach until we had a space-based platform like Kepler. But to talk about Kepler isn't to talk about sun-like stars at all, right? So this is one of my favorite figures from the entirety of the Kepler mission, and it's because it's such a surprise. So this is showing the number of stars, or the number of planets per star. This particular figure from 2012 is at orbital periods closer than 50 days, but this analysis has since been extended out to an AU. So the number of planets per star as a function of stellar effective temperature. So here's what we knew prior to the launch of Kepler. For stars that are about 5,800 Kelvin, and planets which are about 10 times the radius of the Earth, which are lumped in with this blue curve here, there's about 0.01 planets per star. So that's what we knew prior to Kepler, and all of these planets awaited Kepler. Of course, stars burn hydrogen into helium across both ends of this x-axis. But there's a reason why we're focused here. It's because Kepler's primary driver was to establish the frequency of Earth-sized planets orbiting sun-like stars. And that's clear when you look at these numbers across the top, which show the number of stars that went into the bin in each of these calculations. So even though it certainly appears that the smallest planets seem to occur more often around small stars, Kepler observed only a tiny handful of them in comparison with the sun-like stars that it observed. And that's because we did not know at the time that these small stars host planets in greatest abundance. They host small planets in greatest abundance, and moreover, they themselves are the most ubiquitous type of star in the Milky Way. So M-dwarfs, so-called M-dwarfs, which are things cooler than 4,000 Kelvin and smaller than half the mass of the sun, are 70% of the stars in the Milky Way, about 40% of the mass, and they're 0% of the baryonic mass, and 0% of what you can see with your naked eye. So even though these stars are a galaxy's silent majority, you can't see a single one. And if you could see at infrared wavelengths, and your eyes were sensitive to dimmer light, you would see 7 or 8 stars appear for every star that you can see with your naked eye, and those stars host small planets. So it stands to reason the odds are against us as living creatures actually being around a sun-like star.
So it takes into account the fact that the fractional dimming by Earth-sized planets for the smaller stars would be larger, so it would be
they're
biased.
easier to see. Yeah. So in order to produce an occurrence rate figure like this, you have to take into account the sensitivity of the instrument. So if it transits, would you have seen it? As a function of spectral type, how big would that signal have appeared? And also the geometric probability. How often, if there is a planet at that orbital separation, did it produce a transit at all? So let's return to the solar system. So now I've argued a typical type of planetary system in the Milky Way doesn't orbit a sun-like star at all. It orbits an M-dwarf. Now, what about that planetary system? Does it look anything like ours? And by ours, I mean our solar system is roughly coplanar, and the orbital spin axis of the planets is more or less close to the spin axis of our stellar rotation. So the largest degree of misinclination between any one of the inner 8 planets between any 2 of the inner 8 planets is about 7 degrees. But if you took the orbital inclination difference between every single pair of planets, it would look like a Rayleigh distribution, and it would peak around 2 degrees. So we are relatively flat. Looking interior to the orbit of Mars, this is showing a top-down view of the terrestrial planets in our solar system to scale, relatively speaking. And now I'll show here just a bouquet of the type of multi-transiting systems that were detected from Kepler. So if you have a very flat planetary system, it stands to reason, sometimes you don't just see one planet transit, you see more than one planet transit. And we can compare now, in broad swaths, the solar system, the stellar system, which is best known to us, and the planetary system Kepler 186, which perhaps is a blueprint for planet formation in the Milky Way by virtue of it being a small star. And if you look at sort of like if you squinted from very far away, these planetary systems aren't so different. Our sun has 8 planets give or take, at least 2 of those planets, give or take, are in the habitable zone, or coplanar within 7 degrees. And for Kepler 186, we know there must be at least 5 planets because 5 planets transit. They must be coplanar to within 8 degrees, given the fact that all of them transit. And yet at least one of those planets resides in the star's nominal habitable zone. But these planets are parked much closer in. So I decided to devise a test. This is showing a graduate student from Yale I worked with for a while. He produced a lot of movies to highlight some of the interesting problems we were working on. This is a top-down view of a typical planetary system. It's actually Kepler 11. But you can imagine if a system was perfectly coplanar, generally speaking, you're going to see more planets transit. And if those planets have additional dynamical excitation and there's a higher mutual inclination between planet orbits, on average, you will see less planets transit. And this was the single observable that I used to conduct a study about the average type of planetary system in the Milky Way orbiting an M-dwarf with colleague John Johnson. So this is showing all of the data that we used for this study. This is showing as a function of the number of transiting planets per star, how many host stars within Kepler were detected. So of course, the vast majority of M-dwarfs observed from Kepler host 0 transiting planets. Not because they don't host planets, because the geometry doesn't work out quite right. So we devised a test, which is if you could carve a stamp of a planetary system, and you could draw on only 2 parameters, the number of planets per star and the scatter in their mutual inclination. If you carved that stamp and you stamped it isotropically all over the Kepler field of view, what would you expect to see? And moreover, what would that stamp look like to best recover the number of transiting planets per star that Kepler saw? So this is what we concluded when we tried one single population of planets. And what I want to point out first is that this type of model in which you have a highly populated planetary system with a high degree of mutual inclination doesn't furnish a very good fit to the data. So that's the first thing to observe. We also have dynamical reasons to think that this isn't a particularly sensible distribution because we know, or a particularly sensible type of planetary system, because we know from separate radial velocity information from planets detected from the gravitational reflex motion that they induce in their host stars, that heavily populated planetary systems tend to have very low eccentricity. And from equipartition, we should expect that low eccentricity also traces low mutual inclination. So this is also like a little bit unusual.
But this prediction in detail must also depend on the period distribution you assumed.
Yeah, we used a flat period distribution from Dan's paper, actually. I remember at the time.
But in principle, you could put your kink between 2 and 1 in with the period distribution too, right?
You could vary the period distribution too, but there didn't seem to be reason to do that.
I see.
You know, from other observational constraints on period distribution. But we also assumed, like you can also actually just look at the ensemble of planets orbiting M-dwarfs and see that it looks more or less like flat in log AU space. So that's including the geometric.
And one other question here, isn't the number of systems with 0 planets also a strong constraint on this model?
Yes, it is. So it's also a good constraint. You could get out.
But you did not use it in this paper, right? You did not use 0 planets.
No, we didn't. So the way that we compared with what was known, so at this point that we published this, there was a known underlying occurrence rate of M-dwarf planets, which said there are between 2 and 3 planets around every star. So we didn't use 0 in this particular paper, the 0 transiting planets per star. But what you would infer from what we determined from the mixture model is if every single star hosts a planetary system and they are divided into some mixture, we infer on average you would get between 2 and 3 planets per star. So what we found was consistent even though we didn't fit to the number that hosts 0. So what we decided to do was the next most simple thing, which is to adopt a mixture model. So saying that maybe there isn't necessarily just one type of planetary system, but rather 2. Now we're marginalizing over 5 parameters, which is the number of planets in the first type of system, the number of planets in the second type, the average mutual inclination, or the peak of the Rayleigh distribution in the first type of planetary system and in the second, and the fraction of the time that they occur in the first versus the second. And this is what we found, which is that these two, there exist 2 populations. There's evidence for it. The ratio of evidence is about 100 to 1 from the M-dwarfs alone. and that they're very well separated in population space. The solar system would reside around here. So it would reside in this first population. And about a year later, the TRAPPIST system was found. So this planetary system also resides right around here. These are extremely flat planetary systems that host many stars. From here on, I'll use the term compact multiple to refer to that.
And does the scatter and mutual inclination mean anything when you have one planet per star?
Oh yeah, what does that mean, right? So to talk about non-integer numbers of stars, generally speaking, we were really careful about how we define that in the paper. So let's say, what does this number even mean, 1.5 planets per star? It means 50% of the time you have one planet per star. Then mutual inclination isn't well defined, it doesn't matter. But 50% of the time you have 2 planets around that star, then mutual inclination is well defined. So this is just showing the marginalized posterior distributions on these quantities. I'll point to the bottom right-hand corner, which shows that the fraction of the time that nature seemed to make planets, this is among Kepler host stars, seem to be around 50%. However, these types of planetary systems are really overrepresented in transit surveys, and that's because there's more planets that can potentially transit, and when you have that many planets per star, and you have assumed some flat spacing and logarithmic intervals with their periods, you're just getting more planets close in, where nearly all of the transit probability resides. So this is showing sort of a schematic about what the Kepler yield of planets looked like around M dwarfs, if I had to take a guess. So this is showing the number of planets per star. The dark blue shows when they're transiting. And I'll note another piece of information I included here, which seemed to be, although this has recently been more called into question. Originally, a paper by Morton and Wen argued that in the multi-transiting systems, the orbital, the angular momentum vector associated with the orbits of the planets appeared to be very well aligned with the stellar spin orbital momentum vector, and it was misaligned in the multis. However, that hasn't necessarily held water, but it certainly was suggested. So even though these types of planetary systems, the so-called compact multis, are 50% of the planets in the Kepler survey, like I said, they're overrepresented. They're only about 15 plus or minus 5% of M dwarf planetary systems. This is showing the result that we derived, that John and myself derived from using the number of transiting planets alone per star. Phil Muirhead did a paper that same year, published a project that same year using different observables, and concluded the same thing. So the question is then, now that we know that nature produces planetary systems in abundance around small stars, we needn't necessarily establish that fact further. Now we know the planets are there. The question is, where are they nearby? Kepler looked at only a fraction of the sky, and the average M dwarf that Kepler looked at is 100 light years away. So if those planets are there, statistically, if they're around every single M dwarf, if the planetary system resides around every single M dwarf, then where are the nearby ones? And this is the question being answered by NASA's TESS mission. It was launched in March of last year. So every single one of these observation sectors, of which there are 4 kind of stacked on top of one another, is about the size of 4 original Kepler fields. And it's in a very different type of orbit. So rather than having that exquisite sensitivity to transiting planets out to 3 years, such as the Kepler mission had, the TESS field of view pivots every 27 days. So this is a very different footprint on the sky, and therefore a very different completeness to transiting planets. But it doesn't mean you can't address what the underlying ensemble completeness is going to be for M dwarf planetary systems. This is something that I derived from work by Peter Sullivan, who did an incredible, exquisite job of figuring out how the TESS detector should react to incoming photons. That wasn't work that I wanted to reproduce. It was great as it was. However, in that original paper, they assumed a model for planet occurrence that was unimodal. And I don't think necessarily that would produce a realistic predicted transit yield, given the fact that 15% of M dwarfs host planets really close in, and those are the planets that TESS will almost certainly be strongly biased towards seeing, by virtue of the fact that it looks only 27 days at a given star. So I extracted this completeness function, which is to say, as a function of radius and period for the TESS M dwarfs on average, how likely is it that the planet will be detected in TESS? I took this mixture model for planet occurrence that I derived, and we reproduced a prediction for what TESS would see, namely that we ought to expect about 50% more planets than was previously predicted, and that 20% should be multiply transiting systems. And that's because TESS's extremely strong bias for planets in short orbital periods means that now 75% of the planets in the TESS yield will be derived from compact multis, even though these are only 15% of stars in nature. And we can make dynamical predictions too, namely that TESS planets on average are going to be much dynamically cooler than Kepler planets. And I'll say that in the original work, there was a prediction that there should be 0 multiply transiting systems. And TESS already found its first compact multi around an M-dwarf. It took months. And that's because these systems are so common in nature. So this is showing now sort of a breakdown of what we think the TESS host stars will look like. I'll say too that TESS will miss, on average, something like 100 transiting planets out of an average 200 stars around which TESS sees a planet. So said another way, take an average 200 stars around which TESS detected a planet. There will reside, under TESS's detection threshold, additional planets lurking. This is where follow-up missions such as Spitzer can come in. So with predictions like this, you can make arguments like there will be additional undetected transiting planets in the TESS light curves, and there can be an extremely strong synergy with ground and space-based follow-up. Namely, if you had, for example, a small ground-based suite of telescopes that had even modest completeness to transiting planets out to a couple days, and you looked at 200 TESS hosts, you should expect to find 7 plus or minus a couple additional transiting planets. And that's a small ground-based survey to do that, but you need predictions for what TESS will see. There's another prediction one could make that a student is working on right now. Her name is Janelle Gonzalez-Quiles. I advised her last summer. She'll be going to Johns Hopkins probably to start her PhD program in the fall. And there's a prediction from planet formation theory between 2 quantities which might be seemingly disjoint. And that's the adjacent Hill spacing between planets, so the orbital spacing, and the bulk density of those planets, which is a prediction that we can test based on a comparison between the Kepler and TESS fields. So now that we know the types of planetary systems that TESS is likeliest to see and the likeliest Hill spacing between planets in those 2 types of missions, we can map that to a predicted bulk density for the planets and show, on average, that TESS planets should be much fluffier than Kepler planets too. So this is something we can also prove or disprove based on radial velocity follow-up and atmospheric follow-up that Janelle is leading the project. So I've made an argument about the type of planetary systems that reside most often in the Milky Way, but how dynamically stable are these systems? I've talked about this 15% number, but with hundreds of M-dwarf planetary systems, you can begin to ask, where does this come from? Why is this here? Why are 15% of planetary systems this way? And my first attempt to answer this was in a study led by Jack Moriarty, who was a graduate student at Yale. And we produced a suite of N-body simulations to address 2 questions. So these are simulations in which we used hunks of rock, so very late stage planet formation, hunks of rock intermediate in size between asteroids and the moon. And we distributed them according to 2 parameters. The first being the total amount of mass available in these particulates, and secondly, the surface density power law that defines how those particles are distributed in the disk. We integrated them forward in time, and we asked 2 things. First, can you take a variety of formation conditions alone and reproduce the 2 types of populations that Kepler saw, using these 2 parameters alone? And secondly, are systems frozen in once they form? So do you find evidence for the fact that after the systems form, and then a gigayear goes by, an average system is going to self-destruct? So what Jack found is that 2 types of disks alone can explain what's going on, where the first type of disk ought to be more steeply distributed matter, or more mass available total, and the second type of disk ought to be flatter, or less mass is available. I should say too that there is a prediction, which is that you should then see a separate metallicity distribution between these 2 types of planetary systems, which I'll visit in a couple of slides. You can also make a prediction. So these 2 types of disks self-consistently reproduce a number of Kepler observables, being the number of transiting planets per star, other important things such as the ratio of periods of adjacent planets, and their transit duration ratios, which is probing how long it takes the planet to sweep across the face of the host star. If you normalize those quantities between multiple planets in the same system, you're probing how planar they are when they cross the face of the star. And you can make guesses too about what the eccentricity should look like in these types of systems. So this is showing now what we would predict for the contribution from the hotter mode, which is to say less planets per star or more highly mutually inclined, and this cooler mode that furnishes compact multis. So now I'm going to overplot a figure from Vincent van Aylen from very recently. I'll say too that we really want planetary systems around M dwarfs to reside at lower eccentricities. The reason for that is because being very close to an M dwarf, close enough that water is in its liquid form, means also that you're close enough where even a modest eccentricity can induce enough tidal heating to sterilize the surface of it. And this is what Vincent found when fitting separately the eccentricity distribution of singles and multi-planet systems. So this is showing what he would have predicted for multi-planet systems, so-called compact multis, and what they what they measured for compact multis and what they measured for singly transiting systems. So I'm making an argument here, which is that phenomenologically this is a workable model. And we concluded two things: not only that you can explain everything with a variety of these two types of formation conditions, but also that you can do it self-consistently. And there's another thing, this is the first time I'm announcing this particular result, which was really exciting. I made an argument that if there's a difference between these two types of planet formation conditions, you should see a difference in metallicity. There was a result that came out from colleague John Brewer last year, arguing that more compact multis form around metal poor stars. But in that paper, he kind of played fast and loose too with radius. And we also know that metal richness is correlated with the number of Jupiters that nature produces. So it was sort of a mixture of these two interesting parameters, whether or not nature forms planets at all, and then whether it has hot Jupiters and so on. So we wanted to compare apples to apples, which is to say, is there a difference in the types of metallicities of host stars that host multis and host singles? So this is now showing a color magnitude diagram. It's generally speaking hard to extract the metallicities of M dwarfs, and there have been a lot of comparisons between single and multi-transiting planet systems and their metallicities. But we have an advantage here with M dwarfs, which is that you can extract their metallicities pretty well on a color magnitude diagram, and you can do it not only for the planet hosts, you can do it for all of the M dwarfs in the Kepler field. Then you can see, is there a difference, an offset between the metallicity and the compact multis and an average star? This is showing color on the x-axis, where redder goes over here and bluer goes over here. The reason why metal-rich and metal-poor M dwarfs tend to separate this way in these particular colors are because of really strong titanium oxide absorption in these two bands that produces the metal shift, and this is showing the absolute magnitude in Gaia, which corresponds here to spectral type. Metal-poor stars over here. So this is what this undergraduate found from a summer project. This student was advised by Jason Dittman, who's my colleague at MIT. So what I want you to notice, first of all, is where most M dwarfs lie. Now, keep in mind that M dwarfs that host zero transiting planets, they still host planetary systems of some kind, but probably only 20% of them are compact multis. So compare that distribution to this red population, which is showing just compact multis. So where just comparing the singles and the multis, you can't really discern reliably enough, it's like 2 to 3 sigma, that they're the same population. But comparing the compact multis with all underlying M dwarfs, which is a new trick, shows that they really are offset. And I think speaks to something about their formation condition. I can make a guess about why lower eccentricities result in compact multis, or why it's imprinted upon them. But simulations can also trace volatile retention too. So I've argued that with these suite of simulations, we can reproduce a lot of observables. And there's a reason to believe that you can also map how volatiles move through the original disk, like how they get transported, and then whether they last. So using work from Hilke Schlichting's team at UCLA, we're starting to paint on how much of surface volatiles should get lost at every impact in these same simulations, and see how much should remain. This is work led by Kadri Chance, who I advised at a summer program at Harvard and is now a PhD student at Vanderbilt. However, I really want to take an agnostic approach. So I've made an argument, which is that I think formation conditions alone explain the variety of planetary systems seen, the average type of planetary system seen in the Milky Way. However, I want to be as neutral as possible in the sense that, wouldn't it be great to devise an observational test to see whether or not that's so? So it's one thing to make an argument that this model self-consistently reproduces what's seen. However, Are there other possible models which are supported by the data? And we really wanted to test one in particular. By we, I mean myself, Dan Tamayo, and Jim Davenport. This other hypothesis is that nature forms systems that look like compact multis 100% of the time. These are metastable on a gigayear timescale. So what happens is as time goes on, they decay, and they turn into this other type of planetary system. And there's some theoretical evidence for this existing. So this is showing a plot from Pu and Wu from 2015, showing how this original number of compact multis gets diminished and diminished about every decade in log time until you're left with the population that we see today. However, what a shame that would be, one might argue, for the evolution of life in the Milky Way if most M-dwarf planetary systems, which form in a dynamically cool fashion, so cool enough that eccentricities could still allow atmospheres to survive over long timescales, self-disrupt, to be more eccentric on the timescale that we think life takes to evolve. However, this is testable, and we decided to do this being as agnostic as we possibly could be. So taking into account only the fraction of compact multis today, what might the decay function look like? If such a decay function exists, what decay functions are supported given the observed data today, which is that about 15% of planetary systems are compact multis. So we reverse engineered what types of stability functions are feasible. So it's possible in nature, and I would argue it's my favorite hypothesis, that nature tends to just form them that way. 15% of the time, I think probably from formation conditions. However, it's also possible that 100% of planetary systems around M-dwarfs, almost every planetary system in the Milky Way, forms looking like TRAPPIST, looking like the TRAPPIST system. It self-disrupts on a time scale that has a half-life of maybe a gigayear, and then produces the distribution that we see today. I've overplotted here what that Pu and Wu decay time scale might look like in comparison as a function of the age of the star. Ideally, what you could do to answer this question is just ask, are the hosts to multiply transiting systems younger on average? That would answer everything. Then you would know right away, well, it seems like age plays an effect. More youthful systems tend to be more intact, and older planetary systems tend to be more excited. This is incredibly hard to do, although other folks are making efforts, such as I think it's right here, at CCA, on dating planetary systems. But we can use a trick with M-dwarfs, and it's the fact that M-dwarfs have kind of a Boolean activity fraction, or a Boolean sort of like activity indicator, where they're either active or they're not. Work by Elizabeth Newton shows that that transition happens really quickly, and it depends on the spectral type. So even though stars like the sun are active only for a second, relatively speaking, of their lives, some M-dwarfs, including the lowest mass M-dwarfs, are active for a Hubble time. So if you can locate a population of M-dwarfs which are active over a timescale of the decay that you're interested in, you should expect a difference in the planet population between active and inactive stars. So here's how we did that. So we allowed to vary the fraction of compact multis at formation, the slope of that decay, which is the most interesting physical parameter here. So there's all kinds of reasons within planet dynamics to think that different dynamical timescales are at play. Timescales from a single orbit all the way to a Hubble time. So once you no longer have mean motion resonances that overlap, you could have secular resonances that overlap over 10 gigayears. So this could be an independent constraint on which physical processes are most important in the disruption of planetary systems, and also the time at which this hypothetical sculpting, if it exists, ceases. And we asked, dependent upon this stability decay timescale, what would the TESS field of planets look like around active versus inactive stars? The reason why we couldn't do this with Kepler is, first of all, because Kepler did not look at enough stars, and secondly, because it was looking at stars mostly at spectral type N0, which are active only for a half of a gigayear or so. So we don't have enough active versus inactive stars to compare, and also we would only be able to test stability timescales half a gigayear or less. So what we're showing is that depending on what timescale we're interested in, we can look as a function of spectral type and test whether the raw planet occurrence rate is higher around active or inactive stars. What's crucial here for folks who are most interested in M-dwarfs and probably have this question hanging in their minds, so what we found is that the TESS occurrence rate around planets, just the number of stars that host planets at all, should appear to be about twice as high around active stars depending on what that stability timescale looks like. This is showing sort of like toy models of medium and fast decay. We define it a little bit better in the paper. And also depending on what the true compact multi-rate is, so we're also marginalizing over our uncertainty on what that number actually is. In nature, you should see twice as many planets around active stars. The reason why this matters for folks who are interested in detecting planets around M dwarfs is because it's much, much harder to see planets transit at all around active stars. So the fact that this goes the opposite direction, we already know it's going to be harder to find planets around active stars. However, if we detect twice as many around active stars, then that goes the opposite direction of selection bias and is a feasible measurement to make. So I've made an argument now, first of all, that M dwarfs are extremely common planet hosts. They host a variety of planetary systems, some of which might be more intrinsically habitable than others. And also, I think they're dynamically stable over long time scales based on formation conditions. However, if they're not, that will be answerable in short order. But there's another question here, which is what is the longevity of atmospheres around these stars? And I'm talking about atmospheres around the most interesting type, a planet, which is a small planet which is cool enough that it might have liquid water. And in order to introduce this idea, I'll refer to one of my favorite studies in exoplanetary or planetary science from the entire time that I've been studying this field, which is actually in the solar system. This is an image of Saturn's moon, Titan, gathered by Cassini. In a study that was led by Ty Robinson, they did a very ingenious thing, which is to take the Cassini spacecraft and align it in such a way that Titan's atmosphere is backlit by the sun. And you can use a trick, which is what color photons are permitted to pass through Titan's atmosphere and reach the detector versus which are absorbed by the atmosphere. That way you could detect the types of molecular species that are present in the atmosphere without having to go there, which is the only way we can hope to detect what's present in exoplanet atmospheres. The difference with Titan is that we actually did go there. This is a crucial proof of concept that this way of understanding the content of atmospheres in other worlds actually works. This is showing the transmission spectrum of my wildest dreams for an exoplanet. And it's many decades away. But for Titan, what we're seeing here is as a function of wavelength, how physically large, basically, does the planet appear? So imagine that Titan was just a hunk of rock. Rock is an equal opportunity absorber of photons. The planet should appear to be the exact same size regardless of the wavelength that you look at it. However, if there's an atmosphere on top of Titan, Titan will appear physically smaller at wavelengths where that atmosphere is optically thin, and the world will appear physically larger at wavelengths where that atmosphere is optically thick. But superposed on top of these beautiful ringing methane features from Titan is also a Hayes power law that encodes the average particulate size in Titan. In this case, tholins, which are like sort of goo, or it's hard to define tholins. It was Carl Sagan who coined the term. They're photolized carbon atoms, so basically gunk and dust is what's present in Titan's atmosphere. What's incredible about this study is that we know the average particulate size of what's in Titan's atmosphere because the Huygens probe tasted the particulates when it visited Titan. And we know about how high these features should be. It probes the surface gravity of the moon from the speed at which Huygens plummeted to the surface of Titan. So these produce consistent results, showing that this is a feasible way. We've known within exoplanets that this is our best hope within the near term anyway, of detecting the species in other atmospheres, but it really works for Titan. And moreover, Titan's spectrum is information rich, which has not been the case for a lot of exoplanets. So this is showing the planet I referred to really early on in this talk, which is 2.5 times the size of Earth, about 500 Kelvin. It orbits an M dwarf. These are the exact same axes as for that Titan figure. So as a function of wavelength, how big does the planet appear, relatively speaking? The colored lines here are our models from atmospheric theorist Eliza Kenton. The real data from Hubble's WIF-C3 camera is shown here. And what you can see is that this planet is not giving up its secrets. So if we ever want to know what the atmosphere of GJ 1214b is made of, we will either have to observe it enough times to see whatever really high mean molecular weight features still appear, or we will have to go there. So it appears that there's maybe a really high altitude cloud deck, which is gray, preventing us from seeing any difference in the optical depth of different colors. It could be that there's some lofting mechanism, getting really high, getting very large particulates, bigger than a few microns, up into the stratosphere of GJ 1214, but think of the risk. I mean, this is the major way in which folks in the exoplanet community talk about detecting the content of the atmospheres of other planets, is using really long campaigns in transit with the James Webb Space Telescope of exoplanets. This is showing a mock-up of one of those. Again, it's the same axes as a function of wavelength. How big does the planet appear? This is the best possible scenario. This is an extremely bright star, a really small planet, or a smallish planet around a really small star. With a campaign they showed here of 30 hours, you're starting to see features which might correspond to biomarkers such as water or CO2. However, the most typical case will probably be 200 hours. So if you have James Webb time for 200 hours on a pretty bright M dwarf, like 10 parsecs away, and you want to be able to detect water at a signal to noise of 10 or 15, 200 hours should do it. Issue is that 200 hours is already a big ask for any tech, but the issue here is that those 200 hours each hour has to be brewed in transit. And the planet only transits once every few days, in the best possible case, if it resides in the habitable zone around a really low mass star, or further away. So we're talking about really a calculation of risk assessment. Which planets should be picked? Do these planets retain atmospheres at all? And what I contend is that we can constrain this with data that's already in hand. And this was a study led by MIT graduate student Sherry Woe. So we decided to take data in hand from planets, which we think are the most interesting. So these are planets which are between 1 and 3 times the radius of the Earth, between 3 and 500 Kelvin, and in orbit around low-mass stars. Well, if it's so easy to get data about those things, why haven't we seen a number of spectra about them, a number of spectra of them in the literature already? They're so rare to come by. We decided to do it with 30 extremely similar planets and try to eke out an average measurement. We aren't trying here to constrain the presence of any one individual atmospheric feature with 2 data points. However, you can make an argument that an atmosphere exists at all if those 2 points are different in any way. So if the spectral slope is negative, perhaps there's some kind of haze. If it's positive, maybe it's some molecular absorption. However, it means not only that the atmosphere is there, but unlike GJ 1214, the atmosphere is observable. It's eminently observable. So, and we can kind of anchor that power law with Kepler, the optical transit from Kepler, and with the transit at 4.5 microns of Spitzer.
Sarah?
Yeah.
Doesn't this require one to know the temperature distribution pretty accurately in order to do this model, right?
Yeah, we're really planning. I mean, this is a very big bin that we're throwing planets in. So it's, do atmospheres exist on planets that are between 1 and 3 Earth radii, between 300 and 500 Kelvin? Do. So this is also like, that's a very big bin of planets, where Earth and Venus are so different, and yet they're so close to being the same size and the same mass. And yet this is the type of thing that's possible today. Also, I wasn't trying to make an argument about our detailed or fine understanding about individual planets. The question is, will this James Webb time be useful at all? Do these atmospheres even exist around the type of planets to go and look at them with a type of fine-tooth comb that would require a more detailed understanding? Yeah.
So wouldn't you also want to take into account like how quiescent the star is? So a lot of M dwarfs are very flary and bursty, and they can have strong winds, and that could strip an atmosphere. So is that something you also take into account, or?
Almost all of these are around M0s. So they're not active for super long, but what you're speaking to is 100% right. It's been impressed upon me over and over again by folks who work in exoplanet atmospheres around M dwarfs, is that a UV photon matters much, much more than an optical photon. It matters much, much more for what the photochemistry will be, which means that, if I had my pick of future spacecraft, for example, if we're actually interested in characterizing the atmospheres of these planets, you need to understand what's happening in the UV of the star. And it's totally possible, furthermore, that because M dwarfs are active for so long, all atmospheres are stripped. But this is testable. So this is what Sherry found. Sort of skip to the results here. This was just showing the ensemble of planets and their relative size in comparison with Earth. So as a function of this sort of number of planet systems, arbitrary number here on the x-axis, this red is showing the Spitzer transit depth, the black is showing the Kepler transit depth. So crucially, we find internally consistent Spitzer transit depths. This is an issue with Spitzer often with interpreting transit depths is that it can be different one from the other. We think we did it in a careful way. And you can imagine that if the Spitzer transit depth is deeper than the Kepler transit depth, you should see this positive spectral slope. That corresponds to a transmission spectrum which slopes upward. And if the Spitzer transit depth is shallower, that's a negative spectral slope. Now turn this ensemble of data on its side. What Sherry found is that we can assume, we can fit one distribution for what this power law looks like. It peaks around 0, which makes a lot of sense. However, it doesn't do that good of a job of reproducing this really long tail up here. So what we adopted is the next most simple thing. So we find with modest confidence, with about 20-to-1 ratio of the evidences, that the best fit distribution using a single distribution isn't favored as compared to a dual model in which 80% of atmospheres are indistinguishable from flat or bare rock, with the quality of the data we have, which makes a lot of sense. However, some fraction of the time, atmospheres are inconsistent with flat. And this corresponds to a positive spectral slope, so it's a molecular absorption of some kind. And this is a conclusion that 20% of planets around M dwarfs host atmospheres at all. It is not any kind of a claim about what particular molecule might be absorbing at those wavelengths. This is just a claim that these planets have atmospheres, which is crucial, and I know I'll be using it in James Webb in the future. So we favor it by about 20-to-1, and we conclude that this type of planet, which is the type of planet which is going to be appearing the most on proposals from test planets looking at James Webb, have atmospheres, and that those atmospheres, crucially, in addition to existing, are readily detectable by transmissions from metallicity. So I posed these 3 questions at the beginning of my seminar, and I'd like to summarize what I think are the answers to them. So firstly, what's a typical type of planetary system in the Milky Way? It orbits an M dwarf. But there exists no necessarily typical system. Rather than saying there's 2 to 3 planets around every M dwarf, better said is every M dwarf hosts a planetary system of some kind. 15% of the time, those systems look a lot like TRAPPIST. 85% of the time, they look like something else. And we know of about 200 of them so far transiting, that is around M dwarfs, but 1,200 more is my prediction for about what TESS will detect the number of planets around M dwarfs. I think there's strong evidence that formation conditions alone explain this. However, taking an agnostic approach, I've argued based on my work with others that there's a way to constrain dynamical timescales that are interesting in M dwarf planetary systems completely observationally. That's something which will also be really useful in numerical work, because you'll know what timescales are necessary to integrate out to. And finally, we've concluded that at least 20% of cool super-Earths, which is to say between 300 and 500 Kelvin, retain an atmosphere of some kind, and then that atmosphere is detectable, which I think is